Physical spaces hold hidden constraints. Even if you can't see the exact measurements of a structure, the rules of geometry dictate its boundaries. Take a look at this diagram. We have a rectangle containing exactly 90 square centimeters of space. We have one specific constraint regarding its proportions. The length is exactly 3 units more than twice its width. Without a single discrete measurement for any of the sides, how do we find the exact distance around the outside of this specific shape? To solve this, we have to distinguish between two concepts. The area is the two-dimensional space contained inside the bounds. The perimeter is the total distance of the outer boundary itself. You cannot guess your way to the perimeter. Finding the answer requires translating the physical space of this rectangle into the language of algebra. This diagram shows a standard rectangle with direct measurements, a length of 8 inches and a width of 5. To find the area, multiply the length by the width for an internal space of 40 square inches. To find the perimeter, add the two lengths and two widths, 8 plus 8 plus 5 plus 5, for an outer boundary of 26 inches. Symmetrical shapes like squares simplify these formulas further. Because all 4 sides are identical, the area is just the side length squared, while the perimeter is 4 times that side length. Direct measurements make these calculations straightforward. However, practical geometry problems, like our rectangle with an area of 90, rarely provide the dimensions up front. We see this absence of direct side measurements in other shapes. This diagram illustrates a circle with a diameter of 8 units. There are no straight lines to add here. By halving the diameter, we get a radius of 4. This provides the calculations for the area at 16 pi and the perimeter, the circumference, at 8 pi. Imagine a square where the outside boundaries are completely unknown and the only measurement provided is an internal diagonal of 12 feet. Watch how slicing down the diagonal reveals the hidden geometry. The square becomes 2 right triangles. Using the Pythagorean theorem, since the sides are equal, our a and b are the same variable. 2s squared equals our hypotenuse of 12 squared. That simplifies to 2s squared equals 144. Dividing by 2 gives s squared is 72, the exact area of the square. Geometry is modular. By dissecting a shape into simpler pieces, we can use algebra to force it to reveal the measurements it's hiding. Let's return to our original rectangle. It has an area of 90 and a length that is 3 units longer than twice its width. This diagram shows how we convert that description into a rigid algebraic rule. Length equals 2 times the width plus 3. We know the area is length times width, so L times W equals 90. We replace the L with our new rule, giving us the quantity 2W plus 3 times W equals 90. Distributing the W gives us 2W squared plus 3W equals 90. Subtract 90 from both sides, and we expose the mathematical structure of this shape, the quadratic equation 2W squared plus 3W minus 90 equals 0. To solve this, we find two numbers that multiply to negative 180 and add to positive 3, negative 12 and 15. Factoring gives us two possible widths, 6 or negative 7.5. Because physical objects require positive dimensions, we discard the negative value, leaving a width of exactly 6. We plug that width of 6 back into our starting rule. 2 times 6 is 12, plus 3 is 15. The dimensions are now fully identified. The length is 15 and the width is 6. With a precise length of 15 and a width of 6, we have the components needed to solve the original problem. As this diagram traces the boundary, we apply the perimeter formula. We add 15 plus 15 plus 6 plus 6. The total distance around the rectangle is exactly 42 centimeters. We mapped a physical boundary we couldn't initially see by translating spatial constraints into an abstract algebraic equation. Algebra and geometry are not separate subjects, but two sides of the same coin. By moving between them, we can determine the